In our study of finding the derivative of a function, we have developed a number of rules that we have used to help us find derivatives, such as the power rule, the product rule, and the quotient rule. So we're going to look at something called the chain rule. And we use the chain rule to find the derivative of a composite function. So let's write that down. Used to find the derivative of a composite function. Alright, so when you have a composite function, which is basically a function inside a function, then to take the derivative, we're going to have to use this chain rule. So let's look at a basic example. Let's say f of x equals x squared, and g of x equals 3x squared plus 1. Well, the composite of f with g of x is going to be 3x squared plus 1 squared. So remember, a composite function, so this is essentially f of g of x. So a composite function is when we take a function g of x and put it in to this other function, which in this case is x squared. So the question actually won't say, oh, here's a composite function. It'll say if y equals 3x squared plus 1 squared, find y prime. So sometimes a difficult part of using the chain rule is first figuring out that you do have a composite function, that you have a function inside a function. Okay, so let's write out the chain rule. What does the chain rule state? All right, the chain rule states if we have a function f of u is differentiable at the point u equals g of x and g of x is differentiable at x, then the composite function, okay, so we have the composite of f with g of x, which equals f of g of x, is differentiable at x, and, okay, so here's how we end up finding the derivative. And there's two ways. We can say dy dx equals dy du times du dx, or f times g, or the composite of f with g of x, the derivative of that is going to be f prime of g of x times g prime of x. All right. So we're going to go through both of these. If we find the composite function or the derivative of a composite function using the first one, this is what we will call the method of u substitution. And then if we use it using the second method here, that's going to be the inside-outside rule. So we'll say inside, outside. so, and this inside outside, or actually you could probably call it outside inside, doesn't matter. This method, that's not an official name, U substitution, and we'll look at an example of this here too. So let's go back to our problem. We have if y equals 3x squared plus 1 squared, we want to find y prime. So let's first solve this by using U substitution. So first we will use U substitution. Okay, so when we use U substitution, the first thing we have to do is we have to pick what U is going to equal. And in general, you always want to pick something that's inside the other function. So you want to pick the inside part. So because we developed it over here and we know what part was inside, the 3x squared plus 1, that's what we're going to use. So we will say that U equals 3x squared plus 1. Alright, so now we're going to find the derivative of U with respect to x. So that means du dx equals 6x. Now once we've figured out that U was 3x squared plus 1, we now can say that y equals U squared, because that's what we're substituting in for y. So that means dy du is 2u. Alright, so there was another number of steps that went on here. We had our composite function. We had to decide what was u. U equaled, in this case, the inside part, 3x squared plus 1. And we were able to take the derivative of u with respect to x. Then, once we figured out that u was 3x squared plus 1, we were able to rewrite y to be u squared. Because that's what, because we were able to substitute in u for 3x squared plus 1. And then we could take dy du. Right, so now we do this whole process because when we go back to this rule up here, the U substitution rule, it states that dy dx equals dy du times du dx. So notice, dy dx equals dy du times du dx. So let's put in our parts. Dy du, that is 2u. Du dx is 6x. Now the original function was in terms of x, and now we have a function that's in terms of x and u, and we don't want that. So we're going to have to use back substitution to put in what's for u. So we're going to use back substitution. And so in this case, we do know that u equals 3x squared plus 1. So we can rewrite this to be 2 times 3x squared plus 1 times 6x. So then that becomes 12x times 3x squared plus 1. And so our dy dx ends up being 12x times 3x squared is 36x cubed plus 12x. And there is our derivative. Alright, so we were able to find the derivative of this composite function by using u substitution. Now some of you might have caught on. Let me see if I can get this in here. Some of you might have thought, well, if we have 3x squared plus 1 squared, can't we just multiply that out and take the derivative first? And the answer is yes. So we could have multiplied this out. So let's see, that would have been 9x to the 4th plus 6x squared plus 1. And so therefore, y prime would have been 36x cubed plus 12x, which was the same answer as we got. But I wanted to do this example first to just demonstrate the chain rule. And it does show that a lot of times in calculus, there is more than one way to get to the correct answer. So, someone might have said, well, I want to use the chain rule and would have gotten this answer, and someone would say, oh, I want to multiply it out and rewrite it first and get this derivative, and you would have gotten the same answer. So, but just to be clear, both of these would work.